All right, ladies and gentlemen, this is going to be review video 15, representations of phase changes. So the first one I want to talk about is a heat curve. And a heat curve is a graph that's going to show us how the temperature of a substance changes over time as that substance absorbs heat energy. So let's take a look at this graph down here. This graph is specifically the heat curve for water. And you can see that the phases of water are labeled up at the top, as well as these bits here, which are specifically what's happening during a phase change. So let's look at our axes really quickly. Our x-axis of any heat curve is always going to be the heat absorbed over time, and our y-axis is always going to be a temperature of that substance. So as we apply heat to our water sample, it's going to start out as ice in solid state over here. And as we move along, let me change the color real quick. As we move and we absorb heat, we can see that the temperature is rising of that ice. And then we get this flat spot right here. This flat spot represents the phase change. In this case, if we're moving to the right, that's going to be melting. And what I want to point out about that flat spot phase change is that during that phase change, the temperature is actually not increasing, even though that ice/water mixture is still absorbing heat. And the reason that that is happening and we're not seeing a temperature change is because all that heat energy that the substance is absorbing is being used to break the intermolecular forces between those solid ice particles. So if I draw that out real quick and we see our water molecules that are originally in a solid state, we know that there's attraction between those water molecules, and that's the intermolecular force. It takes energy to break that. And so all the energy that the substance is absorbing in this region is actually being used to break those associations. And so that's why we're not seeing a temperature change during the actual phase change. So then once we hit this area, we're at water now, we're at liquid state. And so we're going to keep absorbing energy and keep absorbing energy and keep climbing in temperature until we get to the boiling point of water, in which case we see another phase change flat spot. And then we are still actually going to be breaking the intermolecular forces between water molecules. It's just they're in liquid state now, which means that they're a little bit irregular looking and they're a little bit closer together. However, there's still going to be some intermolecular forces that need to be broken between those water molecules. So we're still not going to see an increase in temperature until that phase change is complete. And then after it is, we're going to see that temperature start to spike again. If we want to go in the other direction, we could look at it in terms of those water molecules losing energy and IMF starting to form as we go to a lower energy state. All right. So once again, I just want to reiterate, temperature does not change during a phase change, and it seems weird. However, there is a reason for that, and it's because of those IMFs, as I referenced earlier, that are breaking during our phase changes. All right, phase diagrams. That's the second type of representation of a phase change or phases that I want to discuss. So phase diagrams, again, it's going to be another graph, and it's going to show us the stable phases of any particular substance at different temperatures and pressures, which at first glance sounds like the same thing as a heat curve, but it isn't. So let's take a look at a generic phase diagram real quick. All right, so our phase diagram looks like this. It looks a lot different than a heat curve. So our axes are a little different as well. This time, you're going to see temperature down here on the x-axis, and you're going to see pressure over here on the y-axis. In the middle, you see a lot of different things. The shaded regions, we have a blue one here for solid, a green one here for liquid, and a yellow one over here for gas. Those phases are always roughly in those positions, though every single phase diagram looks slightly different. You could expect to see them in roughly the same spots. The line itself, here, here, and here, those lines specifically represent the delineation between phases. So depending on which way you move through this graph, it could be sublimation if you're moving to the right, or deposition if you're moving to the left. Or up here between our solid and liquid phase, if we move to the right, we could be melting. If we move to the left, we could be freezing. If we're over here in liquid state and we move to the right, we could get boiling. Or if we're in gaseous state moving to the left, we could get condensation. So again, the lines represent the delineation between phases. And depending on the direction you're moving, you can identify what phase change might be happening. All right. There's a couple of specific terms that I want to point out on here, or specific points, I should say. The first is point B, right there. It's kind of where all of the different phases coalesce and meet at a single point. You can kind of see that because if we were to be right here and moving that way, we could move directly from a gas to a solid, but if we moved this way, we could get to a liquid. If we, it's just kind of like that triple point where all of them coalesce. Technically speaking, what a triple point is when one substance can exist in all three phases at one time. So if I am existing at specifically point B, I could have a substance in all three phases at the same time in the same place, which seems very, very weird. But that's something I'm actually going to show you at some point this unit. We're going to see the triple point of carbon dioxide, and carbon dioxide is going to exist as a solid, a liquid, and a gas at the same place at the same time, and it's really cool to see. The other point I want to talk about up here, undo that. The other point I would like to talk about up here is the critical point. Now, the critical point, you can see something on this graph, how this line between liquid and gas kind of stops. And then there's this red region up here called a supercritical fluid. So the critical point represents the point at which you stop being able to tell the difference between the liquid and the gas phases. They start looking really, really similar at really high temperature and really high pressure. And after that point, we get neither liquid nor gas, but supercritical fluid. And you don't really have to know a lot about supercritical fluid, though you're free to look up information about it if you want to. You just kind of have to know that it exists in general. All right. Now, how can we make a sample change phase? There's a couple of things you can do specifically to make samples change phase. And they're related directly to the axes of a phase diagram. So let's go back up here. We know that our axes are temperature and pressure, respectively. So the first thing I can do to force a sample to change phase is I can change the pressure. If I increase the pressure, what that's going to do is it's going to force particles to become closer together. So let's say that I have a gas phase particle and I increase the pressure of the container around it. If I increase the pressure, what that's going to do is it's going to force those gas particles to be closer together, right? If I put them in a space that's a lot smaller. And when I force particles to be closer together, what I'm actually doing is I'm making it more likely for there to be intermolecular forces between them. And so that attraction between particles that happens naturally is going to kind of cause them to grab onto each other and then drop to a lower energy phase. So I could force a gas into the liquid phase. Or if I'm already in the liquid phase, I could force liquid into a solid phase. Or if I have a gas and I increase the pressure dramatically enough, I could force a gas to go straight into solid phase. If I do the opposite, if I lower the pressure, the exact opposite happens. If I lower the pressure, that's going to allow solid or liquid particles to spread out a little bit more, and they could move to a higher energy phase. So I could force a liquid to go into the gaseous state. I could force a solid to go into a liquid state. Or if I do this hard enough, I could force a solid directly into a gaseous state. So basically what I'm telling you is that you can boil water at room temperature. You just have to lower the pressure on that water dramatically to do it. The other thing that you can do to force something to change phase is a little bit more obvious. You could change the temperature of that thing, right? So we already know that if I apply a bunch of heat to liquid water, it's going to boil eventually, right? So if I increase the temperature, we're going to move that substance into a higher energy phase, solid to liquid, liquid to gas, or solid directly to gas if I increase the temperature hard enough. If I lower the temperature, like if I put liquid water in the freezer, it's going to move to a lower energy phase and freeze, so liquid water would turn into solid. Or if I have steam and I stuck it in a really cold freezer, it would go down to a liquid. Or if I do this hard enough, it could go gas directly to solid. So that one's a little bit easier to understand. There's a couple of terms that I'd like you to be aware of, and these are completely new terms. They're not review terms, but I'm going to introduce them to you here anyway. The first is enthalpy of fusion, and we abbreviate that delta H sub FUS, or delta H fuse. Basically, what that is the heat energy of melting. How much energy does it take to break the IMFs between solid particles? So if we look at solid water, we know that there's hydrogen bonding between those water molecules, forcing it into that kind of pseudo crystal lattice structure. And to melt it specifically, we need to be able to break that IMF. So how much energy does it take to do that? And that's what delta H fuse is, or enthalpy of fusion. Enthalpy of vaporization is that same thing. We're just talking about moving from a liquid state to a gaseous state. So delta H vape is how we abbreviate that. And again, there's still intermolecular forces in between water molecules that are in liquid state. They're just not as clean looking as they are in a solid state. So how much energy is it going to take to break those intermolecular forces? And that is enthalpy of vaporization, or the heat energy of boiling. The last term I want you to be aware of is vapor pressure. And again, this is going to be new to you. And basically what vapor pressure is how much gaseous pressure a liquid sample exerts on its container when that liquid sample is in equilibrium with its gas phase. So that sounds like a lot, but let's imagine for a second we have water in a closed container, right? You have a sealed water bottle and you are able to see through it. If you put that water bottle in a room and leave it alone, you know that some of that water is going to evaporate and cling to the sides of the container and recondense. What that means is, inside your closed water bottle, some of those water molecules are evaporating and some of them are condensing at all times, right? And this is how we abbreviate that. We say that our liquid state is in equilibrium with our gaseous state with these equilibrium arrows here. So here's a nice visual representation of that process, right? So we have all of our liquid particles down here in our liquid water, and sometimes one of them is going to get enough energy and, might get enough energy and pop straight out of that liquid phase into a gaseous phase, and then there's going to be a bunch of water molecules in the gaseous phase cruising around up here. And every now and again, one of those gaseous water molecules might become attracted to its brethren in the liquid state and pop back down into liquid state. All of the pressure up here in the gaseous phase is vapor pressure, right? So we can imagine that different liquids will evaporate easier and different liquids will evaporate less easy or harder, right? Because not all liquids are the same. Water evaporates, yes, and condenses, yes, but other liquids can do it easier, like rubbing alcohol can evaporate easier than water can. Acetone can evaporate easier than water can. So there's a lot of liquids that have higher vapor pressure than water does. So if I, as a liquid, have high vapor pressure, that means that I am easy to evaporate, or I evaporate readily. That means that if I have high vapor pressure, I have a very low boiling point because it's very easy to move from liquid to gas. It also means that my particles have low intermolecular forces, or those attractions between the particles are not very strong, because if it's really easy to break it, that means it's really easy to boil that substance and it's really easy for that substance to evaporate. If I have low vapor pressure, that means that as a liquid, it is hard for me to evaporate. Or it means I have a higher boiling point and I have stronger or higher intermolecular forces. Because again, those intermolecular forces are now much harder to break and I need much higher energy to do it. So it's going to increase the amount of energy necessary to move from a liquid to a gaseous state. And we say that those particular substances have low vapor pressures because not a lot of their liquid molecules are going to pop up into the gaseous state at any given time. All right? So if you have any issues understanding any of this, if you want to ask me questions, please don't hesitate to in class.